In this video, we're going to use our knowledge of how to represent the structures of simple hydrocarbons and how we can modify them in order to produce entirely different compounds. So if we do a little bit of a review of drawing simple hydrocarbons, let's start with the molecule butane. From the prefix but, we remember that this is the prefix that means 4 carbons. So let's go ahead and represent the full structure like this, 4 carbons bonded to each other, and then from the suffix ane, we can identify that this is indeed an alkane, meaning that the only bonds that exist between the carbons are single bonds like this. From there, we can add on hydrogens to make sure that all of these carbons have 4 single bonds with each other. And remember that if you are irritated by the amount of time that it takes to draw the full Lewis structure, we can represent it in line structure form. 1, 2, 3, 4 carbons, and now we are done. Now, is there any rule that specifically states that these 4 carbons need to be arranged in a row like this? For example, if we go 1, 2, 3, and then we put the last carbon here, 4, well, let's go ahead and add on number of hydrogens to make each carbon, to make sure that each carbon has 4 bonds, which would mean that it would look something like this. And after I've added on the right number of hydrogens, we can compare and see whether each of these compounds has the same chemical formula. So 1, 2, 3, 4 carbons and 3 hydrogens on each carbon on the end, which is 6, and then 2 hydrogens on the 2 carbons in the middle. 6 plus 2 plus 2 means that there are 10 hydrogens in total. Now, if we count the number of hydrogens here, we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1 on this central carbon here means that the formula for this is also C4H10. And if we were to represent this in a line structure, we would go 1, 2, 3 for the 3 carbons in the same chain here, and then the last one, 4, would be here. And we can see either way, both of these compounds share the same chemical formula. What we have just demonstrated here is a concept that is relatively common in organic chemistry, which are what we call isomers. If you remember from atomic theory in grade 11, the prefix iso, which is used in the word isotope, referring to 2 atoms that have the same number of protons with a different number of neutrons, you would remember that the prefix iso means same. So these 2 compounds here are not the same because their structures, in that the arrangement of atoms in terms of how they are bonded together is different, but what they share is the same chemical formula, and that's why they are known by the term isomers, which refer to compounds with the same chemical formula with different arrangement of bonds and atoms within the structure. Now, because these structures are different, these specific isomers are, not surprisingly, what we would call structural isomers, because the arrangement of bonds within their structures is different, but referring to the line structure difference as well, which shows the carbon skeleton of the molecule. That's why these are often informally known as what we call skeletal isomers. So to conclude this video, let's try the same exercise with hexane. Well, the first thing we need to remember is how many carbons hexane has. We know from common chemical nomenclature that hex is the prefix for 6. So if we go ahead and write the line structure of hexane, we can go 1, 2, 3, 4, 5, 6, and there is one form. Now, one of the ways to determine the structure of a different isomer is actually to take one of the carbons on the end and attach that carbon onto a different carbon somewhere in the middle. So if we go 1, 2, 3, 4, 5, if we put the carbon that used to be carbon 6 over here, now we have 1, 2, 3, 4, 5, 6 carbons, and if you count, the number of hydrogens will also be the same. Well, what if we were to put the carbon in a different location? What if we were to put the 6th carbon here? Now we have 1, 2, 3, 4, 5, 6, but the arrangement of carbon-to-carbon bonds is different in this form compared to this form here, because this last carbon is attached to a different carbon in the middle. Well, what if we were to do 1, 2, 3, 4, 5, 6? Well, this molecule here looks a lot like this molecule here, and if we just do this, if we flip it around, then it would look pretty much the same here, which means that these two are not in fact isomers, they are in fact the same compound, and you get the general idea. So once again, in summary, isomers are different forms of organic compounds that share the same chemical formula with a different arrangement of bonds that occur within the molecule that give each isomer not only unique chemical structures, but also different chemical properties such as boiling point, melting point, potentially even solubility, and other properties like that. In the next video, we're actually going to learn the naming conventions that exist with more complicated isomers that don't just involve a straight chain of carbons, but involve smaller chains coming off of the side. So before that, to make sure that your basic knowledge of alkanes is solid, see if you can identify the last 2 isomers of hexane and see if you can identify whether this compound here is an isomer of octane, as well as try this case study involving the applications of hydrogen, of which oil extraction is definitely one.